We will continue multivariate normal distribution. Today our discussion will be on two issues. One is statistical distance including constant density contours, constant density contours, and then we will see that how to determine that your data is multivariate normal. So, examination of data for multivariate normality. Okay. So, let us see statistical distance first. Suppose you consider two variable case x 1 and x 2. Now, this is, let it be, this is the origin with mu 1 and mu 2 in that sense. So, let us give this point name as O, and you want to know the distance from O to P. P is another point. What is x 1 1 from 1 and your x 2 1. So, that means this point is from variable point of view x 1 1 1 and x 2 1, or other way the you can write that x 1 2 you can write that manner also. So, then the distance between these 2 points, that is O P, that all of us know that this is x 1 1 minus mu 1 square plus x 1 2 minus mu 2 square in the square root. This is a point with coordinate values. For x 1 this is x 1 1, for x 2 this is x 1 2, and this is the reference point O with mu 1 and mu 2 as coordinate. Then the distance is this distance is known as Euclidean distance. Euclidean distance. Now, let us see that we have several points. We have several points scattered on a bivariate plot x 1 and x 2 in such a manner that it basically resembles like this. The figure is like this, or you can increase this. Okay. Now, if you find out all points equidistant from this O, that is mu 1 and mu 2 coordinate, all points equidistant from O, that means the equal Euclidean distance, and if you join them you will get a circle. So, all points on this circle are equidistant. Okay. Now, we will go to the process level. For example, I told you in one of the classes that we have a manufacturing process, and that process takes certain inputs and gives certain output. This output is measured in terms of its quality. Let there are two variables you are measuring here, x 1 and x 2, related to the output. It may be related to the process also. Okay. For the time being, let us concentrate on the output. Then, if you make a plot of x 1 and x 2, you may get a figure like this. you may get a figure like this. Okay. Now, with little assumption, in the sense that as if the figure resembles an ellipse. Okay. Then I am keeping another observation on x 1 and x 2, which is here closer to this mean point, let it be here. So, as we have assumed earlier also, this is our mu 1 and mu 2. This is one point, let this point is q, and let another point somewhere here, which is p. Correct. Now, if we go by Euclidean distance, OP, the distance between O, the origin, as well, and P, it will be greater than OQ from Euclidean distance point of view. Euclidean distance, what we say is that all points which are equal distance, that will make an ellipse, and this is the, suppose I want to get Euclidean distance with respect to q, OQ, that is the distance, then you will be getting something like this, the circle. Can you make this circle? See, definitely OQ, this distance is less than OP. Correct. Suppose you do not know the distance concept, we are not interested in terms of defining the scattered observation from distance point of view, getting me. Then which one is closer to O, P or Q? Suppose if you see the scatter plot, which one is closer to O, that mu? P. This P is closer to O. The reason is because the general mass, the behavior of the general mass is like this, like an ellipse, and point P belong to this general mass, whereas point Q does not belong to the general mass. So, from the process point of view, this is outlier, Q is outlier, whereas P belongs to the general mass, because our figure is like this, it is like this, your point is here and all values are like this. Instead, your Q point is here, Q and P. It simply indicates that if we go by Euclidean distance measure, we cannot capture this behavior. What is the problem here? The problem lies, see, the variability across x 1 and x 2 is not captured in this equation, and it is because of the variability along the two dimension, the difference in variability, you are getting this structure. So, we want to include variability into the equation. Now, let us see if we give weightage to each observation by its variability, what will happen. Suppose we will now first we will write this OP square in the general sense, x 1 minus mu 1 square plus x 2 minus mu 2 square. X 1 and x 2 are two variables. This is your Euclidean distance, CLEDIAN distance. Instead of this, if I give weightage to the observations by its variability, I can write like this: x 1 minus mu 1 by sigma 1 square plus x 2 minus mu 2 by sigma 2 square. That means, the mean subtracted observation is weighted by 1 by sigma 1 as well as 1 by sigma 2 depending on the variable. So, this one, if I write this is OP square, is it not an equation of ellipse? Definitely, but not this ellipse. It is equation of ellipse, but not this ellipse. Why? Here what happened? There are correlation. So, if we can change. So, this is an equation of ellipse and it represent two variables which are independent like this. So, if I say across x 1 variability high, x 2, then this one is our equation of ellipse, and if you take a point here, suppose this is your P, this one is O is mu 1 and mu 2, and P if say x 1 and x 2, then this OP, this distance is this one. This is the formula for this distance. And as this one is equation of ellipse, all points on this ellipse, the distance will be computed using this function. And what we say here? We say all points on the ellipse are equidistant. This is the all points on the ellipse are equidistant, definitely from O, from a reference point. If you take this ellipse, what will happen? Your OP square, you can write x 1 minus mu 1 by minus or plus, you write whatever may be, they write plus some constant will be coming here, let it be a 1 2 I am giving, x 1 minus mu 1 by sigma 1, x 2 minus mu 2 by sigma 2 plus x 2 minus mu 2 by sigma 2 square. This is the covariance part between the two variables. Okay. This is what is statistical distance. Okay. This is what either this elliptical distance, this is what is statistical distance. So, in essence that the statistical distance, one of the pioneers in developing this is P.C. Mahalanobis. Okay, he is Indian scientist. He is founder of ISI, Indian Statistical Institute. Okay. Now, look at the slide. In this slide, there are in the right hand side there are 4 figures. First, the leftmost one, top one, that one resembles circle. Second one, it basically depicts one ellipse. Third one is also ellipse. Fourth one is also ellipse. But the second and third one, the variability along x 2 is more in case of second one, and in case of third one the variability along x 1 is more, and in case of fourth one it is there are change in variability as well as there is correlation between the two variables. Okay. So, first one is random, in the sense we are saying that the two variables are independent. Second one also two variables are independent. Third one also two variables are independent. Only in fourth one variables are dependent. Now, you think that this is a bivariate case, you think from multivariate point of view. So, when number of variable will be more than 2, then it will be difficult to pictorially visualize, but the points are there. So, ellipse will become ellipsoid, ellipse to ellipsoid. Hyperellipsoid. Okay. So, can you tell me that what is the difference between this figure vis-a-vis this figure? So, if I say this is my quadrant 1, quadrant 2, quadrant 3, quadrant 4, quadrant 1 versus quadrant 3.
In quadrant
1 and quadrant 3.
quadrant 1 and
Quadrant 3. This is quadrant 1, this is quadrant 3.
variability along x axis
Yes.
is more than is less than the variability
Along y axis or x1 and x2. We have given x1 and x2.
and y are uncorrelated.
Uncorrelated. Okay, first quadrant, second quadrant, third quadrant variables are not correlated. Now, what can you talk about the variability of x1 and x2 in the second quadrant? The circle is there. Variables are uncorrelated and variance same. Along x1 and x2 variance is same. So, if x1 x2 variance is same, then it will ultimately resemble a circle. If there is difference in one of the axis, the length will be more, that will be the major axis, other one will be the minor axis. If there is correlation, ultimately the total ellipse will be shifted to other direction. Okay, this is very important concept. Later on in principal component analysis, we will again bring back to this figure. There we will see that if they are highly correlated, what is the need of measuring so many variables? Can we not measure a smaller number of variables? That we will discuss. Okay. I think if you look into this figure you have seen earlier also, and this equation also you have seen earlier. What is the exponent part of a multivariate normal bivariate normal density function? This is the exponent part, and we have also discussed that the exponent will resemble an ellipse. So, that is the distance. This is what is the statistical distance. Okay. What will be the distribution of this exponent part? Yes, it is chi-square. Why it is chi-square?
X minus mu by sigma, that square. So, that is basically the
Yes, x minus mu transpose, then sigma inverse x minus mu, that is the exponent part, and minus half is there, we are not considering that minus half. You see this x minus mu transpose and x minus mu, that is the square term of normal variable, and this capital sigma is the variance part, covariance part. So, what your capital sigma is population sigma, it is a constant value. So, the square of normal is your what is square of normal is z, and z follows chi-square, the linear combination of z follows chi-square distribution. So, this will follow chi-square distribution, that what we are saying, probability that this value will be less than equal to chi-square p some alpha value, this will be 1 minus alpha. Now, in this equation mu, sigma are population parameters and x is the random variable. and your chi-square distribution will be different types. The shape of the chi-square distribution can be like this, can be like this, can be like this, depending on the degrees of freedom. And you all know how to see chi-square distribution. Chi-square distribution, degrees of freedom is there one side, and other side the probability values. Then we will discuss contour, what is basically constant density contours. You see this figure carefully. This is bivariate density function. This is the mu, that is the bottom reference point, you just see that is coming through. If you just see the from the top, if you see what you will see, you will first see the point for this top point. Then if you come little distance lower and take a cross section, then you will be seeing this ellipse. If you come even little more, you will be getting the second ellipse. Like this, you will be getting different ellipse, and as we have already discussed that all points along this ellipse is equidistant. We have proved this one by statistical distance, they are equidistant. So, here what is happening, that's why the total data set, the total data which is represented by this MND, here it is basically bivariate normal distribution, and you are capturing now. Now, the more you want to include more number of observations, your ellipse will be bigger. What does it mean? What I am trying to say, suppose your case is like this, your case is like this, this is the case. Now, if you take this, you take like this is your cross section here, this is the cross section, then what is the portion you are considering? You are considering a smaller portion. If you take a cross section here, you are considering a bigger portion. So, as a result, what is happening? Your ellipse is becoming like this. So, I can say this may be 25% ellipse, this is maybe 50% ellipse, this one may be your 75% ellipse, this may be 95% ellipse. What does it signify? It signifies that 25% of observation will be on or within this ellipse, 50% will be within or on this ellipse, 75% will be on or within this ellipse, and 95% will be on the ellipse, and that is what is this one alpha. If you choose alpha equal to 0.05, then you are creating an ellipse in such a manner that this will be 95%, 0.95. That means, you are considering 95% observations to be within or on the ellipse, rest 5% will be in other, out of this region. So, why we are saying this one is constant density contours? What is why we are saying this is constant density contours? What is contour?
So, actually these are the footprints of constant density loci. If we take the locus of the constant density, we will get a
Elliptical region.
These are the footprints.
This is the plan. That is why I said, if you see the plan view from the top, you see in the floor itself the footprints will be generated, and equal distance points will be making one ellipse. Why constant density contour? What is the contour? A contour line of a function of two variable is a curve along which the function has a constant value. This is Wikipedia definition. So, our function is f x, f x1 x2, that is the function, and we are taking, when we are making a cross section here, that means we are taking a constant distance, constant density, and suppose you are taking this 0.5 as the density, then along this that 0.5 we are making a cross section, and that cross section will bring certain ellipse here also. And as a result, we are saying that this is constant density. That means all the points on this ellipse, this is constant density, having constant density.
So one minute, sir, giving the definition,
Hmm.
when you have seen shown the Euclidean definition.
Hmm.
So there is a contour line of a function of two variable, a contour line of a function of two variable. But sir, contour should be generally for n number of functions.
Yes, yes, it can be. It is not that only two variable case. For example, we want to draw a contour on the world map for the cities having equal altitude. That means from the mean sea level, you will find out the city's distance, that altitude value. If you join a line, that is also contour, distance contour. Similarly, temperature contour, same manner. It just you think here what is happening, you think from a hill point of view, this is a hill. Now, from the floor of the hill, bottom of the hill, you are going up, and after certain height make a cross section. As this is the height, suppose this is my floor, this is the height. So, this is the density, you are making a cross section there. Need not be that it will be a two variable function of two variables, it can be function of many variables, and ultimately our case is multiple variables only. Here one example. Consider the data given in example 1. Obtain constant density contours for alpha equal to 0.05 and alpha equal to 0.01, and we have seen that the d square, this is x1 minus 100 by square root of 10 square, this one we have given earlier. Considering this equal to chi square alpha. Now, when alpha equal to 0.05, then this will be chi square 0.05, variable is 2. So, degree of freedom is 2, and you have to see this value. What is this value? This value is 5.99. So, now this is the ellipse, this is the ellipse which is basically taken into consideration chi square 2.05 5.99, means we are this is the ellipse what is basically constant, all the points having equal density value. Now, how do you get this 5.99 value? This is what is the chi square distribution, and when your degrees of freedom for that distribution is 2 and our value is 5.99, see this is 0.05 5.99 this value. If it is 0.10, then your value will be 4.61. So, ellipse will be little smaller. Okay. Any question from your side?
Suppose in case of two-dimensional data, we have an inclined ellipse as you shown. Here x and y are correlated. Now, what is the degree of freedom? Is it 1 or 2? I think it is.
No, that degrees of freedom case is purely dependent on the number of variables considered. Whether they are correlated or not correlated, it is immaterial.
But sir, at the time of correlation, the distribution should be should the distribution will change?
No, the ultimate exponent value will be different, because distribution will not change.
That chi square distribution means z square, basically summation of z square, but now that separate terms will also come if there is a value of correlation.
No, that will not be, that is not correct. If there are p variables, then our case is e to the exponent is this one, e to the power minus half transpose this one, you are talking about this part, this part. Whether there is, because this is covariance matrix sigma, so definitely there is correlation or covariance. We are considering this correlation component or covariance component. This here basically if we say this, we are not going to statistic, it is a population domain. So, this expression is chi-square distributed.
So, number of variable involved equal to
Degrees of freedom always. Okay. So, that means what we are saying, that x minus mu transpose this x minus mu, it is chi-square p. Now, I think your question is, suppose if you go for some transformation of the variable, then your number of variable will reduce because of correlation. Suppose if the data is correlated, when you go for principal component analysis like analysis, what will happen? Your number of dimension will reduce.
Actually, I thought the rank of the covariance matrix, that is the number of independent variable, should be the degrees of freedom.
No, here it is not like this. Here the covariance component is well accounted for the derivation part. Okay. Now, we will discuss another important aspect that is very important for all of us, that when we collect data, suppose we collected data n cross p and our data points are like this. We are saying that we have collected the data from multivariate normal population, MN population mean multivariate normal population, and we are defining that our x is multivariate normal with p variables mu and sigma, the population parameters. What is the guarantee that your data is multivariate normal? It is true that if your population is multivariate normal, the data you generate, that will be multivariate normal also, but you do not know, you do not know whether that population is really multivariate normal or not. So, what we do there, we examine the data to understand that whether data comes from multivariate population or not. So, in this case, in multivariate domain, we will use chi-square quantile plot, QQ plot, chi-square quantile plot. Q stand for quantile. What is quantile? Any idea? You know median. So, how do you get the median? Your data point, you first order the data from smallest to largest ascending, and then you find out the middle location, and you say if this is my variable x and what is the middle value of x, that is median. So, when you are making median, how many parts you are making for the data? 2 parts, okay, 50-50. So, this is one side, this is another side. You know quartile, quartile will make partition the data, total data into 4 parts. This is my quartile 1, quartile 2, quartile 3, quartile 4, and we know that Q1 and Q3 is the interquartile range that we have discussed in descriptive statistics. So, when you make quartile, you are making partitioning the data into 4 parts. Now, you do one thing, you partition into 100 parts. What will happen? Sorry. That is percentile. So, median, then you are saying quartile, then you are saying percentile. Suppose I do not want like this median quartile, I want to partition the total data set into n parts. Then what name you will give? You cannot give, you have to have some name, that is quantile. So, that means if you partition the data into two parts, the median, that is also quantile, general name. Quartile is also quantile, percentile is also quantile, and if you partition even more or less number than the 100 parts, then that is also quantile. So, by quantile plot, we want to see that how multivariate normality will be assessed. Okay. For example, suppose you have collected n data points, 1, 2, 3, n data points you have collected. Let the data is x1, x2 on xp variables, and I am sure all of you are in a position to fill up this. Now, we will calculate the d square value, Mahalanobis d square. Mahalanobis d square. I am writing this one as d I square, where I stands from 1 to n. Correct. So, what is this? So, you have some reference point somewhere. That reference point definitely, if it is a p variable case, then it is the mu vector, mu 1, mu 2 like mu p. You are getting on p variable, you are getting, this is your first observation, this is your second observation. So, like this, if there is ith point, you will be getting x I 1, x I 2, x I p. So, this is your ith observation. Now, you want to find out where does that ith observation lie. Mean if we consider a two dimensional case, this is my mu 1 and mu 2, then somewhere here this is my ith observation is falling. So, I want to get this distance. I think we have discussed the statistical distance part. What is the formula for statistical distance? X minus mu transpose sigma inverse x minus mu. Now, in Mahalanobis distance, the formula is x minus mu transpose S inverse x minus mu. Getting me? So, when I say d I square, I am saying x I minus mu, but I do not know the mu. So, I will write x I minus x bar S inverse x I minus x bar. So, if you write in this format x minus mu transpose and this sigma to the power minus n x minus mu, in the this is the exponent of the multivariate normal distribution, that also follows chi-square distribution, that is the general statistical distance. But when I say this is S inverse, this is we say that Mahalanobis has developed this. So, for every observation you can get this distance. Okay. Now, x I is what? X I is x I 1, x I 2, x I p, p cross 1. So, x I minus x bar transpose S inverse x I minus x bar, what will happen? What is this? This is 1 cross p, S inverse will be p cross p, and this one will be p cross 1. So, resultant will be 1 cross 1. So, you will be getting a value I am writing here, suppose this is d1 square. For the second one, you calculate d2 square, same formula. Like this, you will be getting di square, then dn square. Correct. So, what are the steps then? You have collected data. There are n multivariate observations. We want to compute the distance of each observations from the mean vector. Here we will be concentrating on the sample mean, that is x 1 bar, x 2 bar like x p bar, that mean. So, you require to calculate this mean vector. You also require to calculate the covariance matrix. Once you know this, you require to calculate S inverse. This also will be P cross P matrix. Once you all those things you have computed, then you go for di square. For I equal to 1, take this row, first row, put here, every observation will be subtracted by the corresponding mean. Okay. Then then you go for the second one, third one, like this. And using this equation, you are n number of distance values. Now, depending on the observation value, it will be different types. For example, what I mean to say, now from a set of multivariate observations, you calculated the distance and finally, you got data matrix like this, d1 square, d2 square, di square, then dn square, that is what data you got, and this one I am saying this is my d square matrix. So, what you require to do now, you have to find out the quantiles. Please remember, we say quantile plot. So, if you require to know the quantile, the one of the issue is you have to arrange these values, observed values in ascending order. So, if I say my ascending data for the distance values are like this, d within bracket 1 square, within bracket 2 square, like this, d within bracket I square, like within bracket n square. This is my ordered data. So, you will be having smallest to largest data set. Fine. Now, how many data points you have? N data points. You create n quantiles here. So, your 1, 2. So, you are now partitioning the entire data, this data, transform data, distance data, partitioning this distance data into n quantiles. What will be the distribution of this di square? What is di square? X I minus x bar transpose S inverse x I minus x bar chi square, correct. So, this follows chi square as p variables are there, p. Then as I know the d square is chi square p di square, and what you have created? You have created a data matrix now, different data, that is n cross 1 transform data d, and which is chi square distributed. So, that means all those this can be a chi square axis. I can get for quantile all points chi square value I will be getting. Now, di square is chi square distributed. So, from di square, if I compare with the chi square quantile values, I must get a relationship. Understood or not? This is nothing difficult. suppose this is my chi-square distribution. For example, let like this is your chi-square. You know the lowest value and largest value from the data set, it is known. What is this chi-square value? If I say I want to know this chi-square p, what will be this value? You require to know then what is the probability right hand side, getting me? So, if I know that what is the probability of this, and if I subtract by 1, I will be knowing the what is the probability of this. So, with respect to this probability from chi-square table, you will be getting this value. Similarly, for the second quantile value, you will be also getting, third quantile value you will be getting, because you have n data set, this chi-square axis is partitioned into n parts. So, everywhere, so I am saying that you have chi-square 1, chi-square 2, this 1 and 2 not degrees of freedom, these are the observation, that is the quantiles. So, like this you will be getting chi-square n values. Now, as we said that d square is chi-square distributed. So, there will be relationship between d square and chi-square. If you plot d square in this side or di square and chi-square in this side, you will be getting a straight line like this. Okay. You may get here, may get, it will be a straight line, linear relationship. Now, see the problem given here. See, this is my data set bivariate case. We have considered 10 points, 1 to 10, and this is my first observation 93, 52.33. My second observation is 94, 53.46, like this. What we have done? We have calculated the distance for this observation, first observation, from the mean value x1 and x2, that mean value you have to find out, and from that mean value, and then using the distance formula di square equal to xi minus x bar transpose S inverse xi minus x bar, we computed this value 2.25. So, my first observation is 2.25 distance apart from the mean. My second observation is 1.40 this distance apart, unit distance apart from the mean, like this 102 and 63.71, this is the 10th observation, is 3.57 units apart from the mean. Okay. Understood? Now, this is the calculation part only you have to utilize this formula carefully. If you use this formula, you are in a position to get this. This is your first step. What is your second step? Second step is order, because you want to find the quantile values. So, you order, that is ascending order. Okay. Third one is you find out the chi-square quantile value. What is this? Chi-square p n minus I plus half. This is the chi-square quantile value. What is happening here? You see that you have 10 data points, I equal to 1 to 10 data points. So, these 10 data points ordered data points. So, that means your this is the chi-square axis, let it be, this is the chi-square variable axis. So, you have divided into 10 parts, 10 parts, 1 to 10 parts you have divided, and what will happen? Your chi-square will be something like this we have discussed. Now, what you want to get the chi-square value here. So, first you find out the probability value here, right hand side you use, because we will be using table. Then for that probability value you find out the chi-square value. That is why what you are doing here, you are writing chi square p n minus I plus half. So, if I want to do little more manipulation here, what is n minus I plus half? N is 10, we have taken 10 data points. So, this is 10 minus 1 plus half, 9.5. So, we want to find out the probability. So, how many data points are there? 10 data points are there. So, if I divide by n again, so that by 10, so this, that means this will be 0.95, and this one also you write this was by n, because this probability value you want to, this is the probability value, alpha value. So, your first one, first chi square, this value is chi square 0.95. What is this value? You see here, .1. Then what will be the second one? 10 minus 2 plus half divided by 10. This will be 8.5, means 0.85. So, your second value here you find out for chi square 0.85. 0.85, chi square 0.85 is 0.33. So, third one will be 0.75, 0.58, 0.65, chi square 0.65, 0.86. So, like this. Then what we have done here? Then we have this side di square, y axis, x axis chi square value, and when you plot these two, you will be getting this type of straight line. Getting me? So, clear that your total data set is this, your total data set is this one. Every observations is transformed into one value, aggregate value, that is the Moulin-Bésch d square, and you are now finding out the distribution for this, and we all know this is chi square distributed. Using this property and the steps like this, plot. If you get a straight line, that is multivariate normal. If it differs substantially, then definitely that is not multivariate normal, but there will always be some amount of departure. So, what is that departure acceptable, that also you have to check. So, there are some other methods for checking also, like KS test is there, Kolmogorov Smirnov test, D max. So, you will be able to check all those things. Okay, this is what is our in totality the multivariate normal distribution we have discussed along with the properties. So, as it is very important one. So, first of all you must know that your multivariate normal density is 1 by 2 pi p by 2, then your covariance to the power half e to the power minus half x minus mu transpose sigma inverse x minus mu. Okay. And definitely your all j x j less than equal to infinite, j equal to 1 to p. So, there are two parts, one is constant and another one is exponent, and it is exponent which is very important. So, the exponent part x minus mu transpose epsilon inverse x minus mu, it follows chi square p. This distribution is chi square p, and this is also known as constant this will give you the constant density. This will give you constant density. Now, in and this formula is chi-square, this is chi-square, but this quantity resembles an ellipse. Okay. This will be an ellipse when p equal to 2. For more than p equal to 2 variables, it will be ellipsoid. Okay. Then there is another concept called statistical distance. Keep in mind, this is very important concept, and constant density contours. The properties of multivariate normal distribution is important. Properties of MND, that if x is, what we said properties, if x is multivariate normal, then x j will be univariate normal, that we have seen, j equal to 1 to p. Now, if x is multivariate normal, subset will also be multivariate normal. So, that means, if I create a subset x cube 1, that will be q, mu q and sigma q. Then linear transpose of x, this will be your univariate normal with A transpose mu, A transpose sigma A. If you find out q linear transpose, then that will be your multivariate normal, that is A transpose mu. Only the matrix multiplicability, compatibility part from multiplication point of view you have to check. Okay. And then finally, when you collect data, the data must be examined and you have to check that whether data is coming from multivariate normal or not, and that is possible through chi-square quantile plot. There are other plots also, but we will be looking into this. Okay. So, I have given you one data set, that 5 variable data set. If you can find out whether the data coming from multivariate normal or not using the statistical distance concept, or you take your own data set, just test, use Excel or MATLAB. Okay, thank you.